All right, welcome back to the deep dive. We're all about getting to the bottom of complex topics, really understanding how things work. And today we're diving into something that's absolutely crucial in aviation. Weight and balance, specifically for those big birds, the aircraft weighing over 12,500 pounds at takeoff.
Yeah, we're talking about the heavy lifters of the sky. And it's fascinating how these massive machines can take to the air and fly so gracefully. But it all boils down to carefully managing weight distribution, making sure it's balanced just right for safe flight. We're going to break it all down for you today, pulling from FAA guidelines, aircraft manufacturer manuals, and even looking at some real-world operational examples to show how it all comes together.
Exactly. And the goal here isn't to make you an expert in aircraft weight and balance overnight, but to give you that solid understanding of how it's calculated and, more importantly, why even tiny adjustments can make a big difference, a surprisingly big difference in how an aircraft handles.
It all starts at the very beginning, right? When a brand new aircraft rolls off the assembly line. One of the first things that happens is a meticulous weighing process. This establishes the aircraft's basic empty weight and pinpoints its center of gravity. And that center of gravity, or CG, is like the balance point of the aircraft.
It's kind of like, I don't know, if you try to balance a ruler on your finger, that point where it stays perfectly horizontal, that's its center of gravity. And knowing exactly where that point is on an airplane, that's essential for its stability and how it responds in the air.
Precisely. And, just like our own weight can fluctuate, an aircraft's weight isn't a constant either. Things like modifications, even those that seem minor, can shift that crucial CG. That's why the FAA and other regulatory bodies mandate reweighing under certain conditions, because any alteration that affects weight or its distribution can impact that critical balance.
And the rules around reweighing, they can be a little tricky. Like, let's say an aircraft changes operators, and both the previous and new operators had approved weight and balance control programs. As long as the last weighing was within the past 36 months, a new reweigh might not be strictly required unless there have been modifications made to the aircraft.
But here's the catch. If that aircraft came from an operator without such an approved program and hasn't been weighed using an accepted method in the last 12 months, then a reweigh is generally mandatory. It doesn't matter if there are no obvious modifications. Flying an aircraft without knowing its exact weight and balance characteristics, that's just too risky.
So we've established why these big planes need periodic weigh-ins. But how do they actually do it? I mean, you can't just wheel a Boeing 747 onto a giant bathroom scale.
Right, you're not going to see that. For these larger aircraft, they use these things called ramp-type scales. They're low-profile platforms that they position under the wheels. And here's the thing. Those scales need to be incredibly precise, calibrated and zeroed out before every single measurement. And they have to undergo regular accuracy checks too, ideally following the manufacturer's recommendations, but at least once every 12 months, even if there's no set schedule.
It's like you were saying before, you can't have shaky data when it comes to something this crucial. So the aircraft is sitting level on these calibrated scales, and they get weight readings from three key points: the left main landing gear, the right main landing gear, and the nose landing gear.
And with those three readings, you can calculate not only the empty weight, which is the weight of the aircraft itself ready to fly, but no passengers, no passengers, no cargo, no usable fuel. But it also gives you what you need to figure out the empty weight CG, or EWCG. And this involves factoring in the distance of each weighing point from a fixed reference point on the aircraft. This reference point, we call it the datum. And the relationship between the weight at each point and its distance from the datum, that creates what we call a moment.
It's kind of like, picture each landing gear pushing down on the scale with a certain force. And the further that force is from our reference point, the datum, the bigger its turning effect, or moment. Now, to make the math a bit easier, we use a reduction factor. We usually divide those moments by a big number, like 1,000. And then we calculate this reduced moment, or moment index, for each weighing point, add them all up, divide that sum by the total empty weight, and finally undo that reduction factor to find the CG location, measured in inches from the datum.
Right. But in the world of aviation, CG is often expressed in relation to the wing, specifically the mean aerodynamic chord, or MA. Think of it like the average width of the wing. And to use the MA as our reference, we need to find the leading edge of the mean aerodynamic chord, the LEMAC. It's basically the front edge of that average wing.
Okay, so now we have another important landmark on the aircraft. And to find out how far behind the LEMAC our CG is, we just subtract the LEMAC's distance from the datum from our CG location. It's all about having consistent reference points.
And then, to express the CG as a percentage of the MA, which is how pilots often think about it, we take that distance between CG and LMAC, divide it by the total length of the MAC, and multiply by 100. So this percentage gives a clear, standardized measure of how the aircraft's weight is spread out along its wing.
So we've got the initial empty weight and CG all figured out. But like we mentioned before, things change. We add cargo, we add passengers, we add fuel. So keeping track of anything that affects the weight and balance, that's super important.
Right. If those records aren't accurate and up to date, you lose track of where that center of gravity is. And how detailed those records need to be, that actually depends on the size of the aircraft. For large aircraft, any change of plus or minus 10 pounds needs to be documented. For medium-sized aircraft, it's plus or minus 5 pounds. And for the smaller ones, even a change of just 1 pound has to be recorded.
So we're keeping tabs on every ounce that comes on or off the aircraft. But how do we figure out the loaded CG for a specific flight? With passengers, cargo, and fuel on board, that's where the loading schedule comes in.
Exactly. The loading schedule is kind of like our roadmap, making sure we're operating within the safe weight and balance limits that are outlined in the Aircraft Flight Manual, the AFM. And it all starts with the basic operating weight, or BOW. This is the empty weight, plus the weight of all those essential operational items, things like the crew, unusable fuel, and other necessary fluids. It also includes a basic operating index, which is essentially a simplified way of representing the aircraft's empty weight moment.
And the AFM, for that specific aircraft, that's where you'll find those all-important Adwirar and LEMAC values. So let's imagine a scenario to see how this works in practice. Let's say our aircraft has a BOW of, let's say, 105,500 pounds and a basic operating index of 98,837. The MAC is 180.9 inches long, and the LEMAC is located 860.5 inches behind our datum.
Okay, so now we're ready to start adding the load for this flight. We have passengers sitting in different sections of the cabin, cargo distributed between the forward and aft cargo holds, and fuel going into specific tanks. And to figure out how each of those loads affects the overall CG, we use loading tables. These tables basically give us pre-calculated moment indexes for different amounts of weight in specific locations.
So let's say for this flight we have, 18 passengers in the forward cabin, 95 in the aft cabin, 1,500 pounds of cargo up front, 2,500 pounds of cargo in the aft hold, and specific amounts of fuel in each of the fuel tanks. Each of these loads has its own moment index listed in those loading tables.
Right, we add up all those moment indexes for the passengers, the cargo, the fuel, and we also add in the basic operating index. And that gives us the total moment index for our fully loaded aircraft. And we do the same for the weight, adding up the BOW, the weight of all the passengers, the cargo, the fuel, to get our total loaded weight.
Then to find our loaded CG in inches after the datum, we use that same formula we discussed earlier. Divide the total moment index by the total weight, and then multiply by our reduction factor, which was 1,000. So for this example, let's say that calculation gives us a loaded CG of 909.6 inches after the datum.
But remember, we want to relate the CG to the aircraft's wing, so we express it as a percentage of MS. First, we find the distance from our loaded CG to the LMAC. That's 909.6 minus 860.5, which gives us 49.1 inches.
And then, to get that final CG percentage, we take 49.1 inches divided by the total MEC length, which was 180.9 inches, and multiply by 100. And in this case, it gives us a CG of 27.1% MEC. And this percentage, that's what pilots use to double-check that the center of gravity falls within the safe limits set out in the AFM. If it's outside those limits, either too far forward or too far back, the aircraft might become difficult or even impossible to control safely.
Now let's shift gears for a moment and talk about operational empty weight, or OEW. This includes the basic empty weight of the plane plus the weight of all those operational items that are always on board, things like the crew, unusable fuel, engine oil, emergency equipment. And when it comes to managing this, operators have two options. They can either maintain individual loading schedules for every single aircraft in their fleet, or they can establish something called Fleet Operating Empty Weights, or FOEW, which basically averages the OEW for a group of identical aircraft.
So if an airline has a fleet of 20 identical Boeing 737s, they might be able to use a single average empty weight for all of them, which could simplify those weight and balance calculations.
Right, but there are some conditions. This OEW, whether it's individual or fleet-wide, it needs to be reevaluated under certain circumstances, after a formal reweighing of the aircraft, for example, or if the cumulative changes recorded in the aircraft's log since the last weigh-in exceed a certain threshold. Specifically, if those changes add up to more than 0.5% of the maximum landing weight or 0.5% of the MXC-CG range. In those cases, the OEW needs to be updated to reflect the aircraft's current weight.
So you're constantly making sure those weight calculations are based on the most accurate and up-to-date information. Now, I've heard that some of the newer large aircraft have a system called Onboard Aircraft Weighing System, or OBAWS. Is that something that gives pilots real-time data on the weight?
Yeah, you got it. OBDUS is a really cool system. It gives the flight crew continuous information about the aircraft's total weight and CG location while they're on the ground. This information is typically displayed as a percentage of MAC, and these systems usually use strain sensors in the wheel axles, a dedicated computer to crunch the data, and displays in the cockpit to show it to the pilots.
So it's like having a live feed of how heavy the plane is and where that balance point sits.
Yeah.
That's going to be incredibly useful for situational awareness.
Oh, absolutely. It's a great tool. But here's the thing. Even though a certified and FAA-approved OBWS can be used as the primary way to check that the weight and balance are within limits for takeoff, it doesn't replace the need for a traditional load manifest. It's more like a really powerful verification tool and a real-time aid. But the detailed planning and documentation, those are still super important.
Okay, that makes sense. So now that we know how much the plane weighs and where that weight is centered, let's talk about how that translates to actually flying the plane. Think about things like setting the stabilizer trim before takeoff.
Right, that's a critical step. The horizontal stabilizer, which is back in the tail of the aircraft, it needs to be trimmed based on the CG location. This basically makes sure the aircraft has the correct pitch attitude for takeoff and helps maintain control during that initial climb. And these trim systems, they can be calibrated in two different ways depending on the aircraft, either in terms of percent MMAC or in something called airplane nose-up units, or ANU.
So let's say our aircraft has a calculated CG at, I don't know, 635.7 inches from the datum. The LEMAX is at 625 inches, and the MSE has a total length of 134 inches. So first things first, we got to find that distance between CG and LEMAX. That's just a simple subtraction, 635.7 minus 625, which gives us 10.7 inches.
Then, to get the CG as a percentage of MS, take that 10.7-inch distance, divide it by the total MS length of 134 inches, and multiply by 100. That gives us 8.0% MSC.
Now, if the aircraft's stabilizer trim system works directly in percent MAC, pilots just set it to 8%. Easy. But some aircraft use those ANU units, and for those, pilots need to consult a chart in the AFM. This chart links the CG position with the corresponding stabilizer trim setting in ANU.
Right, so let's say we have a Boeing 737, and our calculated CG is 8% MAC, with a specific flap setting for takeoff. That chart might say we need a stabilizer setting of, say, 7 and 34 units ANU. It's all about having a clear and reliable way to translate that calculated CG location into the correct stabilizer trim setting. And getting this right is super important because an incorrect trim setting can cause real control issues during takeoff.
Now, we all know that cargo on these large aircraft can be pretty heavy. It makes sense that loading, unloading, or even just shifting it around inside the plane could have a significant impact on the CG.
Oh, absolutely. You're dealing with a lot of weight here, and any changes in cargo position can definitely shift the center of gravity. So let's imagine we're unloading cargo. Let's say we have an aircraft with a total loaded weight of 90,000 pounds and a CG at 22.5% MAC. The MAC for this aircraft is 141.5 inches, and the LAMAC is at 549.13 inches from the datum. Now, what happens if we take out 2,500 pounds of cargo from the forward hold, which is centered around station 352.1?
Okay, so first we got to figure out where the CG is relative to the LAMAC before we touch the cargo. So 22.5% of the 141.5-inch MAC, that's 31.84 inches. Then to find out where that CG is in relation to our datum, we add that distance to the LAMAC's distance from the datum. So 31.84 plus 549.13 gives us 580.97 inches.
Now we got to think about the moments. Multiply the total weight, 90,000 pounds, by the original CG location, 580.97 inches, and then divide by 1,000 to get that moment index. Do the same for the cargo we're removing, 2,500 pounds at 352.1 inches. Then we subtract the cargo's weight and moment index from our original totals. This gives us the new total weight and the new total moment index for the aircraft.
And with those new totals, we can calculate the new CG location. Take the new moment index divided by the new total weight and multiply by 1,000. This time, let's say that gives us a new CG of 587.51 inches from the datum.
Last step, we got to translate that back into a percentage of MMAC. Subtract the LEMAC location from the new CG location, 587.51 minus 549.13, which gives us 38.38 inches. Then divide that by the MAC length, 141.5 inches, and multiply by 100. This gives us a new CG of 27.12% MAC. So as you can see, taking out that weight from the front moved the CG a bit further back.
Now, what if instead of removing that cargo, we just shifted it from one spot to another? Like, what if we took that same 2,500 pounds and moved it from the forward hold at station 352 to the aft hold at station 744.9 on our 90,000-pound aircraft? We know the initial CG was at station 580.97 inches, which is 22.5% MSE. Our MSE is 141.5 inches. The LMAC is at 549.
Since we're not changing the total weight, only shifting it around, we just need to figure out how much that shift changes the CG. So 724.9 minus 352, that's the distance the cargo moved, 372.9 inches. Multiply that distance by the weight that was moved, 2,500 pounds, and then divide by the total aircraft weight, 90,000 pounds. That gives us a CG shift of about 10.36 inches aft.
So the new CG location, that's easy. Just add the shift to the old CG. 580.97 plus 10.36 equals 591.33 inches from the datum. Now let's convert that to percent MAC. First, find the new distance from the LEMAC, which is 591.33 minus 549, which gives us 42.33 inches. Divide that by the MAC length, 141.5 inches, and multiply by 100. Gives us a new CG of 29.82% MAC. So shifting that weight towards the back of the aircraft, as you would expect, move the CG further back too.
Now, it's worth mentioning that sometimes, instead of using a traditional datum, aircraft manufacturers might use something called an index point. It's just a different reference location on the aircraft. And the distances measured from this index point, we call them index arms. So anything in front of the index point has a negative arm, anything behind has a positive arm. But the way you calculate moments and the CG, it all stays the same. It's just a different starting point for your measurements.
All right, so cargo's effect on CG, that's pretty clear. But what about the structural limits of the aircraft itself, like the cargo pallets and how much weight the cargo hold floor can actually handle?
Yeah, that's another key factor, structural integrity. Every cargo hold has a floor loading limit, which is the maximum weight it can safely support per square foot. So when you're loading those cargo pallets, you got to make sure that the weight of the whole thing, including the pallet itself and anything used to secure the cargo, divided by the pallet's contact area with the floor, that number can't exceed that limit.
Okay, so if we have a standard pallet that's 36 inches by 48 inches, that gives us a contact area of 12 square feet. And if our cargo hold has a load limit of, say, 169 pounds per square foot, then the max weight on that pallet can't be more than 2,028 pounds. And that's before you even consider the weight of the pallet itself and any tie-down equipment.
And you can also go the other way around. If you know the dimensions of the loaded pallet and its total weight, just divide that weight by the area to get the floor loading in pounds per square foot. This is just another way to make sure you're not pushing the limits of the aircraft's structure.
So let's talk about payload. This is the stuff that generates revenue, right?
Yeah.
Passengers and cargo. How do we determine the absolute maximum payload for a given flight?
It's not just about how much space you have. You got to consider a few things. The aircraft's maximum weight limits, like its maximum takeoff weight, max landing weight, and maximum zero fuel weight, and also how much fuel you need for the specific trip. So let's imagine a scenario. Say our aircraft has a BOW of 100,500 pounds, max zero fuel weight of 138,000 pounds, max landing weight of 142,000 pounds, and an absolute max takeoff weight of 184,200 pounds. Its fuel tanks can hold 54,000 pounds of fuel, and we estimate we'll burn about 40,000 pounds for this trip.
So first things first, we need to figure out what our maximum takeoff weight is for this specific flight. A good way to do this is take the max landing weight and add the amount of fuel we'll burn. In this case, that's 142,000 plus 40,000, which gives us 182,000 pounds. But we also have to compare that to the aircraft's absolute max takeoff weight, which is 182,000 pounds. Got to go with the lower of the two, so our max takeoff weight for this flight is 182,000 pounds.
Now, let's determine our zero fuel weight limit for this flight. That's the max weight of the aircraft without any usable fuel on board. To figure that out, we take our max takeoff weight for the trip, 182,000 pounds, and subtract the max fuel we could have at takeoff, 54,000 pounds. This gives us 128,000 pounds. But just like before, we got to check this against the aircraft's certified max zero fuel weight, which is 138,000. Again, we use the more restrictive value, so 128,000 pounds for our trip.
All right, so last step, we need to find out how much payload we can actually carry. Take our trip-limited zero fuel weight, 128,000 pounds, and subtract the aircraft's BOW, 100,500 pounds. That leaves us with 27,500 pounds for payload. This is the max we can carry for this flight. And staying within all these limits, that's absolutely crucial for safe operation.
Exactly. Now, let's think about landing. Knowing your estimated landing weight, that's crucial for a smooth and safe touchdown. It affects things like approach speed, the length of runway you need to stop, and the forces on the landing gear when you touch down. Basically, to get that estimated landing weight, you start with the takeoff weight and subtract the total fuel you burn during the flight.
Let's say we have a 4-engine turboprop taking off at 140,000 pounds, cruising at 16,000 feet, where the outside air temperature is negative 32 degrees Celsius. We also know we'll burn about 3,350 pounds of fuel during the descent and landing.
All right, so to figure out how much fuel we burn during cruise, we got to consider the atmosphere up there at 16,000 feet. A standard atmospheric table, like the one from the U.S. Standard Atmosphere, will tell us the standard temperature at that altitude. That happens to be negative 16.7 degrees Celsius. But our actual temperature is negative 32, which is a good bit colder than standard. And colder air is denser, which can affect how much fuel our engines burn.
And luckily, aircraft performance manuals usually have these tables called gross weight tables and a temperature deviation index. These help you adjust those standard fuel flow rates based on how different the actual temperature is from the standard. So using those tools for our specific aircraft and that colder temperature, we can figure out a more accurate fuel flow rate for each engine. Let's say for this example, that works out to be 11,135 pounds per hour per engine.
So if our cruise lasts for 4 hours, total fuel burn during cruise would be 1,135 pounds per hour multiplied by 4 engines multiplied by 4 hours. That comes out to 18,160 pounds. And then, adding that 3,350 pounds we'll burn during descent and landing, our total fuel burn for the entire flight is 19,510 pounds. Subtract that from our takeoff weight of 140,000 pounds, and we get a final estimated landing weight of 120,490 pounds. Knowing this number ahead of time allows the pilots to properly plan their approach and landing.
Now, sometimes a plane might need to land shortly after takeoff, but it's still carrying a lot of fuel, maybe even exceeding its max landing weight. That's where fuel dumping or fuel jettison comes in. In those situations, being able to quickly calculate the fuel dump time is super important.
Absolutely. The goal is to get that aircraft weight down to or below its max landing weight as quickly as possible. So we need to know how much weight we got to lose, the aircraft's fuel burn rate during the dumping process, and how fast that fuel can be dumped. Let's say we have a twin-engine aircraft. Current weight is 171,000 pounds, but its max landing weight is only 142,500 pounds. We know that from the moment we start dumping fuel to touchdown will be 19 minutes. During that time, the engines will be burning fuel at 3,170 pounds per hour each, and our fuel jettison system dumps at a rate of 2,300 pounds per minute.
Okay, so first we got to figure out how much weight we got to ditch. Simple subtraction, current weight minus max landing weight. 171,000 minus 142,500, which gives us 28,500 pounds.
Then, we need to calculate how much fuel those engines will burn during those 19 minutes before we land. So for our twin-engine aircraft, 3,170 pounds per hour per engine, that means we'll burn roughly 2,007.54 pounds during that time.
It's the actual amount we need to dump through the jettison system is 28,500 pounds total weight to lose, minus 2,007.54 pounds fuel burned by the engines. That leaves us with 26,492.46 pounds to dump.
And to find out how long that'll take, just divide the total fuel to be dumped, 26,492.46 pounds, by the dump rate of 2,300 pounds per minute. That gives us approximately 11.52 minutes. That's how long the pilots need to activate the fuel jettison system. Having this info is super important for them to make the right call in an emergency.
Now let's take a look at a smaller aircraft, the Beechcraft 1900, a popular choice for commuter flights. While it's not a jumbo jet, the same principles of weight and balance still apply.
Absolutely. The Beech 1900 is a versatile aircraft, can be configured for passengers or cargo, and just like with the bigger planes, before each flight, a detailed manifest is created. This document carefully lists the weight and location of everyone and everything on board, including the crew, each passenger, and all the baggage.
And to calculate the loaded weight and the CG, we use specific tables provided by Beechcraft. These tables give you pre-calculated weights and moment arms for passengers in different seats and baggage in specific compartments. You also need to factor in the fuel weight, which depends on its specific gravity and temperature.
Right. You multiply each item's weight by its moment arm, and then to keep the numbers manageable, you often divide by a constant, like 100. This gives you a moment index for each item. Add up all the individual weights to get the total loaded weight. Add up all the moment indexes to get the total moment index for the aircraft. Divide the total moment index by the total loaded weight and multiply by that same constant, in this case 100, to find the loaded CG, which is expressed in terms of its distance from the front of the aircraft. or fuselage station.
And just like before, we need to make sure that this calculated CG is within the safe operating limits for the aircraft. That's usually done by plotting the weight in CG on a weight and balance diagram. This diagram shows the allowable CG range for different aircraft weights. If your calculated point is outside of this envelope, you can't fly in that configuration. Something needs to be adjusted.
One interesting thing with passenger aircraft, especially smaller ones like the Beech 1900, is how much the CG can shift just from passengers moving around. Let's say you have a few passengers who decide to move from the front of the cabin to the back. Even though the total weight hasn't changed, the CG will move rearward. You can actually calculate this shift by considering the weight of those passengers and how far they moved. And this is why it's so important for everyone to stay in their assigned seats, especially during critical parts of the flight.
Yeah, and when you get to those really big passenger planes, like a packed Boeing 737-800, managing passenger distribution gets even trickier. They might have assigned seats, but airlines often have procedures and have to make assumptions about how those passengers might spread out in the cabin. Keeping that CG in check is a constant balancing act.
Right, and the Beech 1900 can also be reconfigured for cargo. In that setup, you still use a manifest to keep track of the weight and location of each piece of cargo. The way you calculate the total weight and CG remains the same. And just like with passengers moving around, shifting cargo from one session to another will change the CG. You can calculate that shift using a pretty straightforward formula. Same goes for adding or removing cargo. You got to update the loading chart and recalculate the CG to make sure everything is still within limits.
So at the end of the day, no matter what aircraft we're talking about, before any flight, you got to carefully consider all the weight and balance parameters. Zero fuel weight, takeoff weight, and CG, and the estimated landing weight and CG, and all those values need to be checked against the aircraft's limits to ensure you're not exceeding them at any point during the flight.
Exactly. It all comes down to precise calculations, understanding the aircraft's limitations, and sticking to those established procedures. There's no cutting corners when it comes to weight and balance. It's fundamental for safe flight.
It really makes you appreciate how much impact even seemingly small things can have. Like where people sit or where the cargo is placed, it all plays a role in keeping that aircraft balanced and safe.
And this brings up an interesting thought. We're in an age where technology plays a huge role in aviation. Automation is everywhere. But when it comes to weight and balance, what are those essential skills and that core knowledge that pilots and ground crews absolutely need to have? What needs to remain in the human domain to ensure we're always operating at the highest level of safety? That's something worth pondering.